Hey everybody and welcome back. So today I'm really excited. We get to start to really compile everything that we've been working with up to this point in some really interesting and novel ways. By the end of this section, you're going to have a better understanding of how computers work, how people learn to count in the first place, how other cultures learned how to count, why it is that clocks have 60 seconds in a minute and 60 minutes in an hour. Like all of these odd little bits and pieces of trivia that are floating around were actually critical to human history and mathematical development. And in this lesson, you get to see how all of that comes from some really basic ideas that you're already comfortable with. But if we can look at it in just a little bit of a different way, it's really going to blow your mind. And I'm excited to show you how to do that. So let's go ahead and jump into the notes section for today. This is section R4. So within R4, the first thing I kind of want to talk about is just to start building up our familiarity and some basic ideas that we're comfortable with. So if I was going to ask you, for example, something simple like to simplify or to solve out this equation, let me show you one way that we could think about this. Imagine that you're trying to teach maybe like a 5-year-old or a young family member, or maybe you yourself are trying to imagine what a primitive human being is thinking when they're developing the very origins of math and logic. If we're talking about 3 minus 5 minus the quantity 2 minus 3. There's a lot to unpack here, and really what this came from, ideas like this came from trying to measure quantities of things. That's what we said numbers are often used for, as well as a lack of things or a debt of things. So we could think of one way of modeling all of this quantity as if we are in a sandbox. So let's imagine that we're in a sandbox and it's a perfectly level sandbox. We're going to call this perfectly level state 0. We've zeroed out the sandbox. If I was to create instead maybe like the number 1, I might think of that as being a pile. I have a quantity of stuff. Now if I start from 0 and I create 1, if I'm in the same sandbox, that requires me to have dug a hole. And so this is that idea of balancing equations that you're familiar with. If I am starting with the same idea, in order to create something, I must balance it out with its opposite. But similarly, we can say that if maybe I didn't start with 0, so this would be our example for 0, this would be our example for 1, and then a negative 1, a 1 minus 1, which would also be a 0. Sometimes our sandbox, we say, imagine I had a sandbox that just had the number 2. Well, that would be a sandbox that started with 2 of these piles in it already, and we could begin to make more piles or divide the piles in halves, etc. But this is going to be our base example for what a number is. So if I'm looking at an equation like 3 minus 5 minus 2 minus 3, what do we have there? In this sandbox, we have 3 piles, 1, 2, and 3. We then have the opposite of 5 piles, because the negative means opposite. So that's going to be 5 holes. 1, 2, 3, 4, and 5. And then I have the opposite of 2 piles and 3 holes. Okay, so the opposite of 2 piles would be 2 holes, there'd be 2 more holes, and the opposite of 3 holes would be 3 piles, 1, 2, and 3. Oh my gosh, so it's as if we have this sandbox that has all of these details, but we're trying to simplify it. We're trying to simplify out the sandbox. We don't need all this detail in it. We just need to make sure that whatever we're talking about at the beginning is the same as what we're talking about in the end. Well, I could take these 3 piles and I could use them to fill in these 3 holes here. That would work out just fine. I could take these 3 piles and I could use them to fill in these 3 holes here, and we would be left with a negative 1. So all of this could be equivalent to just simply having 1 hole left in our sandbox. How would we show that algebraically? Well, we have 3, and then we were trying to take away 5, and then we had the opposite of 2 piles and the opposite of 3 holes, which was going to be then 3 piles. So we had the opposite of 2 piles gives me 2 holes, and the opposite of 3 piles gives me 3 holes. So then 3 minus 5 would be if I had 2 holes remaining, I take away another 2, and I add 3, that's going to get me a total of -4 plus 3, which sure enough is equal to -1. So no matter which way you want to look at it, that's really what we're talking about when we're talking about numbers. It's a very intuitive, very natural idea of how do we combine things. And this is what gets us back to some of our earlier topics about the natural numbers, this idea of piles, and then the integers, which includes 0 as well as some of the negative whole numbers as well. And it's the idea of how these all interact that really comes to play here. So now that I've kind of opened up the door a little bit to changing our perspective and how we can see what look like complicated problems as pretty simple examples, let me show you how we can take this one step further with multiplication. Multiplication becomes very difficult when you're first learning it, because when we're originally taught, if you'll remember, if you're originally taught how to do 35 times 24, you might see something like this. Now I'm going to show you how we're taught to do this multiplication, but I want to take a moment and imagine that you're seeing this through the eyes of a 5-year-old, or imagine you're seeing this through the eyes of somebody who's never been exposed to this procedure before. Imagine that you're an early human trying to understand this. Let me show you how crazy confusing this process is the first time you see it. We have multiplication, and what I'm going to do is I'm going to do 4 times 5, and that's going to get me 20. I'm then going to do 4 times 3, and that's going to get me 12. But I'm going to put the 12, and I'm going to have shifted it a little bit to the left for a reason not apparent, except that my high school math teacher told me to. Okay, so we've moved the 12 over. That's fine. I can do that. And then I'm going to start with the 2, and I'm going to do 2 times 5. But instead of putting that back over on the far right, this time that's going to start shifted as well, but I can't put the whole 10 on this line. Instead, I need to put a 10 up at the top here, which is meaningless to the 35. It's just simply being carried, so that stays there for a moment. And then the 2 times 3 happens. That would get me 6, but I can't put 6 in the bottom yet. I need to add the 1 to it, and why I would all of a sudden be adding things isn't immediately apparent, but I'm going to do that, and so that's going to get me a 70. And then I'm going to do addition all the way down, but 0 plus blanks is apparently something I can do now, so I'm allowed to say that's 0, 2, and 0 gets me 4, and then I get 8. So that's going to be 840 is my final answer because of the math magic that my teacher told me. This is not intuitive. Why does this work? Maybe after a little bit of deciphering, we can recognize that there's some play happening behind the scenes with place values, that this is in fact logical and is okay for us to carry out, but the exact reason for it is a little bit odd. Instead, I'd like to show you another way that we could look at this exact same process. Let's look at 35 as being 30 and 5. This makes sense to me. We can look at 24 similarly. That would be 20 and 4. Now imagine that I wanted to have 5 groups of 20 and 4, and I wanted to have 30 more of those groups of 20 and 4. That would give me 35 groups of 20 and 4. That's exactly what this expression says. Let me show you how we can use a picture to help us organize all of these thoughts. I'm going to create 30 groups of 20 and 4. That means I am going to have 30 groups of 20, and I'm going to have 30 groups of 4. I'm then going to add 5 more groups of each. So now I'm going to have 5 groups of 20 and 5 groups of 4. So that's 5 groups that I'm adding in together. To keep all this organized, maybe we organize it like a grid. So now I know that if I have 30 groups of 20, well, do that in your head a little bit and you're going to realize that comes out to a whopping 600. So we get 600 that happens when I have 30 groups of 20. Okay, large number, but it makes sense to me where we got that. If I have 30 groups of 4, you're going to find that that comes out to 120. 5 groups of 20 gets me 100. And 5 groups of 4 gets me 20. And you can kind of separate this out a little bit. So again, we have the 600 that came from groups of groups, and the 120 that came from groups of groups. After all, that's what multiplication means, is it means make groups, repeat this addition over and over again. Well, if I asked you how much I have in total, then you would just simply say I have everything that's shown here. I have 600, I have 120, I have 100, and I have 20. And if you add all of these together, you're going to see that you get 840. Now, I seem to think that this second way is much more intuitive of a method of thinking about what multiplication is, because when I learned about multiplication, like for example, 5 times 4, it was take 4 and then add 4 to it so that you have a total of 5 groups of 4. This is what multiplication means to me, and it's nice to be able to represent it in a little bit more of an intuitive way. Now, by changing our perspective, it also allows us to be able to answer some very interesting questions that would normally be quite difficult. Let me show you something that's kind of cool. If we started off and instead of saying that I want to multiply numbers, what happens if I want to multiply variables? So let's look at something that would normally be a very difficult problem to solve. So we have, let's say, x plus 2 times x plus 3. This can be a very difficult expression in order to keep track of everything, but if we look at it just the exact same way as we did up here, it becomes easy all of a sudden. Instead of looking at 24 as 24, one thing, let's break it up. Let's look at it as 20 and 4. So instead of looking here as x plus 3 as one thing, let's break it up as x and 3. So I have x and 3. And I'm using this number of groups of my x plus 2. Or because multiplication allows us to look at it the other way around, you could imagine the same idea switched. But what we're going to say for right now is we'll have groups, x plus 3 groups of this x and the 2. Let's see if we can't write it like this. So I've got some unknown number x and then 3 more, and some unknown number x and 2 more of those, and I'm trying to do groups of the other idea. Well, let's see if we can follow the exact same idea. They should be numbers. It's just addition and multiplication. Same ideas apply. X times x would get you x squared. We represent that with our exponents. If I have x groups of 3, that would mean that I have x 3s. Sometimes we write that the other way around as 3x's, but I'm going to try to just like play a little bit here. What do we have if I have 2 groups of x? Well, that would be 2x's. And if I have 2 groups of 3, that would be 6. So similarly, if I asked you what happens when I multiply x plus 3 and x plus 2, we would say out of this I get an x squared. I get 3's. I get 2x's. And I get 6. Now some of you may be recognizing that we could rewrite this as 3x's, because x3's and 3x's is the exact same idea. Don't believe me? Let's check it out with numbers. Is 4 times 3 the same thing as 3 times 4? Absolutely. And just to recall some of the vocabulary we learned earlier, this is what we call the commutative property. So via the commutative property, we're allowed to say that this can be written as x squared, 3x's, 2 more x's, and 6, which gives us x squared, 5x, and 6. So as we can see, some of these areas are depending on different shapes. We have one which is a square, one which is a rectangle, one that's just a number, but we can't go any simpler than x squared plus 5x plus 6. What's very interesting is that when you start to write expressions like this, especially the ones that are quadratic meaning anything that has an x squared, a number, we'll say any number, so I'll use a, any number x, and any number b with a regular x, and any number c, that those are actually so common in the real world that they control the motion of stars, atoms, planets, magnetism. They pop up everywhere. If I was to throw my pen up in the air, I would be able to tell you how it's going to behave based on an equation just like this. They happen all around us, and we're going to, throughout this class, be exploring that a little bit more. But why is it that we can't combine them anymore? Sometimes we hear this as not like terms. And by terms, we mean anything that's separated by either a plus or a minus sign. So that's a term, and that's a term. Now, these names, these terms, cannot be combined, and they were originally referred to as nomials. Nomials literally means name. So we can say that nomial either means name or it means term. So when we get an expression that cannot be simplified anymore, we have to call it by many names. We have to call it by a square name, we have to call it by a rectangle name, and we have to call it by a number name. Okay. Now, as you can tell, this leaves us with a lot of opportunity to just play. For example, couldn't I just keep going? Couldn't I just say I have cubes, and I have squares, and I maybe don't have any rectangles, but I do have the number 54 at the very end. Could I express something like that? Absolutely, I just did. How would we talk about these? How would I be able to compare these? How would I be able to categorize and organize these in my brain? Well, this is where we come up with some proper names, and we're going to go through them now just to lend a little bit of clarity. So first thing we're going to say, anything that has multiple names, we're going to call a polynomial. And so the word poly here means many. And you can think of this as appearing in a number of different words. You can think of polyamorous or polygamy, or you can think of it as polymer. All of these uses of poly mean many. So this is just kind of turned into a little bit of like an English root class, but we can say the definition of poly is many. So I can write a polynomial anytime I use many of these names to describe an expression. So for example, I'll just use exactly what I had up here. 3x cubed plus 2x squared plus 54. Now I want you to come up with your own examples over here, but just keep in mind that the way we need to be naming these things has to be in terms of these shapes. It has to be in terms of cubes. It has to be in terms of squares. It has to be in terms of x rectangles. It has to be in terms of just numbers. You can even go further by using x to the 4th and x to the 58th. You can do the expressions, but you can't do anything that isn't a number in front times x to a whole number exponent. Okay, so whole number exponent being 0, 1, 2, 3, 4, etc. All of our natural numbers are counting nature numbers or the number 0. By the way, where does the number 0 pop up in an exponent in this expression? Oh, it pops up right here, doesn't it? This could really be thought of as 54 times x to the 0, because x to the 0 could be thought of as 1. So this could be thought of as 54 times 1, which is just 54. So anytime you have an x to a whole number exponent being multiplied by a real number, that's going to be a name, and when we group many of these names together, we're going to call them polynomials. Okay, let's go through a couple of these other ones quickly. Monomial. Mono meaning 1. So we can say that the prefix mono means 1, so we're going to call something by one name. Maybe I would use a real number. Let's use a complicated one. Let's use something like square root of 2. But then I just need to multiply it by some kind of shape name. So maybe I'll choose x to the 32nd. So I have a 32 degree shape. Okay, so that would be perfectly fine. You can come up with yours. Binomial. Binomial means 2, like bicycle, right? Or binary. So we can say that means 2. So now we need 2 of these shape names to be included. Let's choose something complicated and something easy. Maybe I'll choose the number pi, which is an absolutely real number. I could use pi times x cubed. And then maybe I would say I subtract 2x. Each of these are shape numbers because they're x's to a whole number exponent. Trinomial, like tricycle, means 3. So now I just simply need to have 3 of these shape numbers. I think I'm going to do something simple this time. So we'll do maybe like 3x to the 4th minus 2x squared plus. Those are 3 different shape numbers that are all being created. Come up with your own over here, and as we go through the lesson, come back to this and check to make sure that you've got good examples there when we flesh out these definitions more. So, why is it that we would want to describe all of these things differently? Well, depending on how we are writing these shapes, they allow us, just like in our number example on the first page, to choose what can be combined and what can't. It also helps us to categorize in our mind what kind of shapes these might be that we're creating just from playing around. So let's look at a few examples. If I gave you, for example, the area of a circle. The area of a circle is pi r squared. You maybe have been asked to memorize this in an earlier math class. Well, we also know that a square can be found by taking some kind of side and multiplying it by itself. So we'll call that s squared. That'd be a square made out of the size s. We also know rectangles are going to be anytime where you take a length and a width. Now, all of these give you the sizes of shapes. Specifically, these give you the areas of two-dimensional shapes. We could think of categorizing these in the same way. These are all two-dimensional shapes that we're creating, the areas of two-dimensional shape. Well, instead of saying two-dimensional, let's say degree 2. There's 2 degrees, one for the r, and then another one for the second r it's being multiplied. Here, the s is being multiplied by itself. That gives me 2 different degrees. Here I have an L and a W. Each of those contributes a degree. If the word degree feels a little bit weird, let's go into what it would be if we had a 3rd degree polynomial. So that'd be like a 3D polynomial. Well, 3D might make you think of 3D shape. This is where we're going to get cubes. Look at how cubes have 3 dimensions. They have an S dimension, another S dimension, and a 3rd S dimension. Pyramids, for example, can be measured by length times width times height, and then dividing the product that results by 3. That's how you measure the volume of a pyramid. So we can categorize all these volumes together. And if I was to ask you what would be the number of degrees that would happen in each of these shapes, we would say 3, 1 for each of the variables that's being multiplied together. So we're just kind of categorizing this idea of degrees and exponents into what the shapes themselves would be if we tried to parallel it all back. Okay, let's try to complete a table here and we'll help to organize our thoughts a little bit. So I've got some kind of shape that occurs from multiplying something by itself 5 times. Well, that would be a degree of 5. There'd be 5 different dimensions that this shape has. Don't ask me to draw it, that would be very difficult, but I could imagine that I could create a shape that has this size. The coefficient. Coefficient's an odd word, but you've probably used it before. Coefficient just simply means what is the number of those shapes. Okay, so you can think of it as being the number out front of the term. So I'm going to say that coefficient can be thought of as the number of sizes that I'm trying to combine here. So here, for example, I have one shape that is x to the 5 big. So we could think of that as being, I have one monomial, one name, and that name of this shape can be found by multiplying something by itself 5 times. Let's take a look at this one here. Here I have x, I have another x, and then I have 7 y's. So in total, I would say that this shape was created by multiplying something 7 times over. Not the same thing, but I was multiplying 7 things, and I got 7 as my degree. What's the coefficient? How many of these shapes did I have? Well, if I read this straight out, it would be I have negative square root of 2 x squared y squared. So that means I have negative square root of 2 of these shapes. What if I have pi xyz shapes? Okay, well, pi is a number. Xyz, those are all variables. 3 things that are being multiplied together to give me a degree. So my degree would be 3. And then I have a number of these shapes. Okay, so I have my coefficient of pi. Notice, by the way, that if we go back up here to pi r squared, what this literally means is that if you have pi, number of squares made from r, you will be able to get the size of the circle. That's exactly like what we're talking about down here. We have a certain number of shapes. If we accept that these are shapes and they can measure the sizes of things by multiplying variables by other variables, and that we can get these equations and these polynomials, and that we can represent all of these with pictures, let's see if we can identify whether these correspond with shapes or not. Are these possibly some mysterious shape that we don't know about yet, that we could imagine but that maybe I can't draw? Okay, well, is this one a shape? I definitely have 8 of them, so that would be my coefficient. We can put that down. So I have a coefficient of 8. I have 8 of these shapes. These shapes are made by multiplying x times itself 3 times and y times itself 2 times. So that would be degree 5. That means I have 5 different things that are being multiplied together. So I could say that my degree is 5. Okay, I then am going to take away the number 2. Okay, so I'm taking away something at the very end. That's going to be much, much smaller. So if I'm trying to describe the state and state the degree of this polynomial, let's describe it by its starting point, by its largest degree. So its largest degree is going to be 5. And we would say, yes, this is a polynomial because it has nothing but shapes and sizes that are being added and subtracted from it. So it's a degree 5 polynomial. No problem. Let's now take a look at this one here. First, what is the degree? Well, here I have 5 x to the fifths. So that would be a largest term, or a largest degree of 5. So that would be, okay, degree 5 for that first monomial. The second one is a degree 2. And this one has a degree... This isn't a shape expression here. There's not a shape that you're going to be able to create by division. It's not a polynomial. So this would actually be not a polynomial. So whenever we have a variable that's in a denominator, that's not going to correspond with one of our shape sizes. So we understand that what we're talking about when we're combining all of these different shapes is similar shapes, what we would normally refer to as like terms. Here, when we talk about adding and subtracting polynomials, it's no different. Can I add these amounts to each other, or are they talking about things that are dissimilar? Well, to keep things from being confusing, we can go back to using our piles and our wholes analogy. So here I have 6 x to the fourth y squares. Okay, so that means I have 6 x to the fourth y squares. I'll write that in for right now, so we'll keep that there. And then I have, maybe I'll write that with some kind of shape. So x to the fourth y squares, and I've got some pile that is that big, no problem. Then I have the opposite of a 2xy cubed, okay, pile. That'd be a hole. So I've got a hole here. So this would be an opposite of a 2xy cubed pile. Okay, so far so good. Let's see if I can then do the opposite of a 7x cubed pile. Okay, the opposite of a 7x cubed pile would be a 7x cubed whole. So that's gonna be my 7x cubed whole. And then I also have the opposite of an 8x to the fourth y squared whole. So that would be a pile amount. Okay, so it'd be a plus 8x to the fourth y squares. Now the question is there a simpler way to describe this sandbox? I can't combine items like this and this. I shouldn't say items. What do we have another word for? I cannot combine monomials or terms like these last two because they're not the same size. I don't know how much sand I'll have and a hole left over at the very end. I can't combine an x cubed pile and an x to the fourth y squared pile. I don't know how big those are, and would I draw those as piles at the end or holes at the end? And if so, what would I be left with? That becomes very odd. But if I have 6 x squared y squared piles and I add, that would be to the fourth. If I have 6 x fourth y squared piles and I have 8 more x fourth y squared piles, I do know that that's going to get me a total of 14 x fourth y squared piles. So I could rewrite this entire thing as saying I have 14 x fourth y squared piles, and then I have everything else that I can't combine because I just don't have enough information. So x fourth y squared piles, and then I have minus 2xy cubes, and I have minus 7x cubed. So that's going to be the simplest I can get this. It's just an expression like this. So when we talk about adding and subtracting polynomials, this idea of combining like terms is just, do I have the same apples to apples that I can compare together? And when you read it out loud, you realize that there's a lot of similarities in the language. If I say that I have 5 apples and I add them to 3 apples, you'd be able to tell me that that is a total of 8 apples. If I have 5 fourths, and I wanted to combine that with 3 fourths, you would tell me that that would become 8 fourths. So similarly, if I have 6 x fourth y squares and I add 8 more x fourth y squared, I'm allowed to combine those into 14 x fourth y squareds. Whatever x fourth y squared is, I know I have 14 of them. Okay. So far, so good. We're often going to want to write these to keep it organized, as you can tell, in descending order of degree, which is why we brought it up earlier. It's going to help to keep everything a little bit more organized, and we're going to call this standard form. So this is what we're going to call our standard form. Standard meaning what we're going to default to so that we all understand what the expectation is. So when we look up at this one here, we can see that it's already in standard form because my first term has a degree of 6 from 4x's and 2y's. My second term has a degree of 4, 1x and 3y's, and my last term has a degree of 3. So I can in ascending degree order, and that's just going to help us so that we always alter write things the same way for communication and for ease. We're going to think that that's maybe the simplest way, is to talk about these larger shapes and how they kind of descend all the way down to smaller dimensions. Let's talk about this definition here. Writing down a definition for polynomial of one variable. I really want to encourage you not to worry so much about memorizing. This is the part of the class which maybe you'll remember when you leave college, maybe not, but the skill set I want to teach you is to not be intimidated by expressions like this, because expressions like this pop up all over the world in industry and in technical fields. You don't necessarily know what the phrase is, but you're able to break down what the words are and kind of decipher a pretty general meaning from it that allows you to participate. Here you go. Polynomial in one variable. Polynomial. What's that mean? That is a many named, or we could say, instead of named, we could say term. And instead of term, you could maybe think of like size or shape. I'm going to say shape. It's a many shaped. So we have a many shaped expression. And in one variable means I'm only able to use one variable. Maybe I choose X, maybe I choose Y, maybe I choose Q. But let's say it's a many named term shaped expression using one letter. And I'm going to use letter loosely. Really what we want to say is variable. But if you want to put this down in your notes, this is the way to do it. So how could we write that down? Again, anything that has x to a whole number powers. So we have x to the fourth, we could have x cubed, we could have x squares, we could have x to the first power, which would just be x's, we could have x to the no powers, which would just be 1. And then we could continue to grow this as big as we want. And to help kind of organize this, because we could have many of these x fourth shapes or x cubed shapes or x squared shapes, we're going to say that there could be an amount in front of each of these, some kind of unknown amount. No matter what amount you give me would be perfectly fine. That I have maybe a number ones, I have b x, I have c x squares, I have d x cubes, whatever you want. That's still going to be a polynomial, a many named expression using one variable. Now let's put it all together. How can we talk about these many named expressions, these hidden shapes, as if they were numbers that we could multiply, divide, add, subtract, combine? Well, no differently than we would normally do with a number. We just kind of organize it with our model of logic and then carry it through. So let's take a look here. If I have negative 2 x to the fifths, let's imagine that that's a number. I don't exactly know what the number is, but I can imagine it's a number. So I have that many groups of all of this. So I have groups of 3x cubes. I have that many groups of negative 5x squares. I have that many groups of 1. We can organize all of this the exact same way. Okay, let's multiply it all out. I have negative 2, I have the x to the fifth, I have the 3, and I have the x cubed. What does that get me? Negative 2, and I can multiply that by 3, that would get me negative 6. I have 5 x's that are being multiplied and 3 more x's that are being multiplied. That would give me a total of 8 x's that are being multiplied. Okay, so that's the first part. Let's keep going with our shape. I have negative 2 times x to the fifth times negative 5 times x squared. What does that get me? To be able to simplify that to 10, it gets me a total of 7 x's that are all being multiplied. Let's do the very last one. Well, that would leave me a total of negative 2 x to the fifth ones, or negative 2x to the fifth as my resulting number. So that one's actually the easiest of all, negative 2x to the fifth.